Today we're going to talk to you about Cobalt Strike, and specifically fighting back against Cobalt Strike. So we're going to start off with a little bit of background about Cobalt Strike, talk about what it is, how it's used in the wild, and then touch a little bit on how you can detect Cobalt Strike in more detail. So to kind of jump straight into the background of that. So probably a lot of you in this room are aware, Cobalt Strike is a commercial tool developed by help systems these days, or supported by them, that's used for adversary simulations and red team operations. It was first released in 2012 and is still under active development today. It is, however, also used by malicious threat actors, and there's public reporting about this that dates back to at least 2016. It is something that we commonly see across our kind of aperture, with malicious threat actors using it today, both in our incident response and MDR services. Cobalt Strike is broadly made up of two components, Team Server and Beacon. So Team Server, if you've not seen it, there's an example screenshot on the screen here, is the server-side component of Cobalt Strike. It's the one the operators like Tim will use, where they can interact and issue commands down to the beacons. The beacon is the client-side implant. It's the bit that ends up on the endpoint, and it has a lot of different capability. It's got some built-in commands, as you can see here, which James will touch on a lot more later in terms of like real detection opportunities here. But it also has a lot of flexibility, so you can execute different scripts and tools through this as well. But how is Cobalt Strike actually used in the wild? So Cobalt Strike is actually used by more than 50 different threat groups that are tracked publicly across reporting. There's obviously probably a lot more in private reporting on top of this, but at least 50 in public. This is made up of a mix of both state-based groups as well as cybercriminals. It's commonly observed in ransomware intrusions, as Tim was kind of alluding to earlier. And it's something that we saw earlier this year in the Conti leaks, if you were following those, where ransomware as a service operators will provide Cobalt Strike, along with guidance how to use it and other scripts and tooling, to their affiliates in order to execute ransomware intrusions. In our own kind of incident response space, we do see Cobalt Strike used in quite a majority of cases across our different work. Cobalt Strike is a really configurable framework. You can use it in a lot of different ways. It has a lot of different options. On the screen here, I've got you a little bit of documentation on the left-hand side from the Cobalt Strike systems, which talks about how you configure malleable profiles. So effectively, at a very high level, this allows you to configure how Cobalt Strike operates on both the network, as well as a few different settings on the endpoint itself. On the right-hand side here, I've got the example config pulled from a real ransomware case earlier this year about how an actor was using Cobalt Strike specifically. As you can see on the left, there are lots of different options. You can configure those, but if you don't, there's also default values that get put in there. What you might be able to see, or less so, depending on the font size here, is that on the right-hand side, the config that we pulled from this beacon, a lot of the values are actually the default values. So the actor hasn't changed these, they haven't modified these. And this is something that we do actually commonly see across our aperture, and I'll touch on that a little bit more. So we collect Cobalt Strike beacons, both across our kind of private aperture, as well as publicly from sources like VT. And we will, at scale, extract the configs of all these beacons and store them in our kind of back-end systems. And we then look at, okay, how are actors using these, and is there any kind of clustering or kind of intelligence we can kind of gain from this? And there's actually quite a lot. In this instance, for example, you can see the vast majority of Cobalt Strike beacons are either HTTP or HTTPS. So they're kind of quite common, and they're quite sort of well-known or more towards the default side. When it comes to jitter, which is basically the randomness that gets introduced into the network communication, you can see that in 85% of cases, the default value is used, which is 0. So there is no variation introduced at all. When we look at the spawn to setting, this is the setting that when Cobalt Strike executes tasks as part of post-exploitation, is the process that will be used, you can see that 93% of all configs use the default rundale32 value. That's a lot. This gives you a really good point to look at and potentially a nice detection opportunity, which James will touch on a bit more later. So we've got a bit of a text foo here, but there are stats normally here. This is what happens when you use Mac and Windows and mix them together, unfortunately. What this slide is supposed to show to you is a very nice pie chart. The blue side is the known, and the red side is unknown. So what we do is we look at not only are actors using the default config, but are they using known configs? So there are a number of multiple malleable profiles shared online on GitHub, amongst other places, which are supposed to impersonate or have configured settings that are good for actors to use. So there's some that impersonate Amazon, there's a web bug profile, etc. There's even an APT1 profile if you want to get fancy. We track across our configs that we've collected whether they actually match these known profiles or not through some just sort of back-end kind of analysis. And the blue side, which is supposed to be showing you about 85%, matches against known configs. So effectively, 85% of all Cobalt Strike users that we see is actually using known configs that you can actually sort of know beforehand, so you don't have to sort of find that out. But that red side kind of gives you a hint that not all are exactly known, and not all actors use it the same way. As I've touched on, Cobalt Strike is highly configurable, and there's a really good use case of this, or example of this earlier this year, was Nibelium's use of Cobalt Strike. So for those of you who aren't aware, Nibelium is a state-based threat actor, very much linked to the SolarWinds campaign, which you probably all do know about. This is a quote from a Microsoft report where they were looking into their use of Cobalt Strike. And it's a really interesting and kind of valuable quote where it talks about how much that actor changed between every different victim for their Cobalt Strike usage. They did this to avoid detection, but also to avoid anyone being able to track the kind of wider campaign through this method. So you couldn't link a beacon used on one victim to a beacon used on another. And it does show you that Cobalt Strike can be highly configured, but as I've kind of touched on before, it isn't always the most common for actors to do that. So we've spoken a little bit about what Cobalt Strike is, and if you haven't kind of appreciated before how prevalent a threat it is, or how common it is, and how also relevant it is to all of you in this room, hopefully you do appreciate that now. We speak a lot in defensive circles about detecting behaviors, but there is value in detecting tools as well. And that's hopefully what I'm trying to kind of build that background for you and kind of get through to you. In our managed defense, this is something we've had to face on a day-to-day basis. We've had to build detection for Cobalt Strike at scale. And James is now going to talk through that with you and share some insights from this.
So for the kind of remaining section of this presentation, I'll be taking you through some specific examples about how we can detect Cobalt Strike and other tooling that we often see being used with Cobalt Strike. Before I kind of get into that, I thought it would be worth talking about detection engineering from a strategic perspective, talking about kind of the approach that we use when we're building effective detection capability. If you'll use the examples I've given here, in the top left, you've got maybe your network that you're defending. You've got your crown jewels in your network that you put behind a vault that you're trying to secure, and maybe you have a few detections that sit in front of it. And this is good, but as you can see, there's quite a bit of room for a threat actor to move without potentially being detected. And when we're building effective detection rules and approaches, we really want to build layered detections across the kill chain that complement each other and really restrict the actor's ability to utilize tools, techniques, and procedures. But by restricting their ability to move, we restrict their ability to exist in an environment without triggering a detection and bringing the attention to the blue team. It's also important to use a blended approach of both generic and specific detection rules. So throughout this presentation, I'll be talking about rules that are specific to Cobalt Strike and some of those low-hanging fruits that exist with the default behavior of Cobalt Strike. But it's important to complement those detections with generic rules as well. Because as Callum spoke about, we know that threat actors can and do change aspects of Cobalt Strike. So we need to complement specific rules with generic rules in case they do change it, or they bring in other tooling as well to complement the use of Cobalt Strike. Now, when we talk about Cobalt Strike, as Callum's discussed, we're kind of seeing that actors very rarely change all of the Cobalt Strike's default behavior. And this means there's quite a lot of opportunity for low-hanging fruit detection. And what's really interesting is that some of Cobalt Strike's behavior can't be easily changed. There's a good portion of it that can be changed via the malleable C2 profile that's exposed, but some of its configuration isn't exposed via that profile. And that's where the real value lies. If we can target the parts of Cobalt Strike that can't be easily changed, we can detect its use even if the threat actor believes they're configuring it to a high degree. So, detection opportunities. I'll be talking a little bit about process indicators, talking about how Cobalt Strike leverages PowerShell, talking about how Cobalt Strike kind of exists on a network perspective and how we can use network indicators to detect its presence, what Cobalt Strike looks like in memory, and then also how threat actors can use Cobalt Strike to laterally move across your estate. To kick things off, I thought I'd talk about process indicators. I think process telemetry is by far one of the most abundant sources of telemetry that we commonly see in Windows environments, and it offers a huge amount of potential for detection. Now, as Callum mentioned, one of the most important settings, I would argue, in the Cobalt Strike malleable C2 profile is the spawn2 setting. And this spawn2 setting tells Cobalt Strike which built-in Windows executable to use for certain types of behaviors, such as post-exploitation, lateral movement, and memory injection. Now, by default, the executable that's specified is run-DLL32. And if you were to go and look across your estates for executions of run-DLL32, you would see that in almost all cases, it's executed with command line arguments. However, in Cobalt Strike, the default will mean that run-DLL32 is spawned without arguments. This is a built-in default, and it may sound like a low-hanging fruit, but you'd be surprised how many threat actors don't change this, and this can be a great detection capability for us. So looking for instances of run-DLL32 being launched with no arguments can be a dead giveaway that Cobalt Strike is in use. Now, that's a specific example, but we can actually take this idea further. Modeling how Windows executables exist in your environments can be really powerful. Looking for common parent-child relationships, and then when things differ to those models, can be a great way to look for abnormal behavior. In the same way of looking for Windows executables that are being launched from unusual locations, we've commonly seen threat actors putting executable files that mimic real Windows executables in uncommon locations like C Windows or C users public. Now, I think these next two slides are by far my favorite in the deck, and it talks about parent PID spoofing. Now, for reference, Cobalt Strike has had parent process spoofing since 2017. And I'll talk a little bit about why threat actors and also defenders need to care about parent process spoofing. So if we look at the top left of the screen, this is an example of a typical entry point into a network without parent process spoofing. So if you consider a typical entry point like an Office product, WinWord, Word, it's very common that a user on your estate might receive an email that contains a weaponized Word document. They open that Word document, and a macro is detonated. And that could execute some PowerShell. It could execute a file that's dropped to disk. And so defenders have recognized this. And one of the most powerful threat hunts and detections that we can do is to look for Office products launching unusual child processes. And that's really powerful for us. And as a result, threat actors have responded. Now, when a child process is created, it reports its creating process. It reports its parent process. So in this case, you've got payload.exe that's being created, and it's reporting its parent as winword.exe. And that's a detection characteristic that we can hunt for. Now, some threat actors, and I think just people in the InfoSec community in general, worked out that you can change the parent information that's reported. So in the bottom example, you've got parent process spoofing in action, where you've got payload.exe reporting its parent, falsely reporting its parent, to be explorer.exe instead. It's still being launched by WinWord, but it's falsely reporting its parent to be explorer.exe to break that parent-child relationship. Now, that's a very powerful technique for the threat actors to have. But as defenders, we want to turn this on its head and make it work for us. And this is why I really like this, because we can take a technique that threat actors believes makes them less likely to be detected, and we can turn it into something that really works for us as defenders. So via ETW, event tracing for Windows feeds, you can actually tap into a telemetry set that gives you not only the reported parent process, but the true creator process information. And that's what we're seeing at the table at the top. We can see on the right, the executable being launched is payload, and then moving left, we can see that it's reporting its parent as explorer.exe. Moving further left, we can see that the real parent is winword.exe, which is what we really care about, that suspicious entry point. And what we will detect on is the difference between the reported parent and the true creator process. One of the most effective detections that we have is to look for where the real parent is an Office product, but the reported parent is not an Office product, because that would indicate to us that someone's trying to break that relationship and trying to hide something from us as defenders. Now, there are some Windows executables, legitimate Windows executables, that do exhibit this behavior. Werfault.exe is a great example of this. With some fairly simple kind of exclusion work and some noise reduction, you can exclude these results, and you then have a very high-fidelity data set to build your detection rule sets off of. And I really want to hammer home how powerful this has been for us. This is something that we see threat actors using because they believe it makes them less likely to be detected, and we've been able to build this into a very powerful technique for us. If you are interested, I put a link in the bottom left. It's a blog post that we wrote, shameless self-plug. But it goes into a lot more detail about the types of telemetry feeds that you can tap into and how you can build this out into a powerful detection opportunity. Next up, I want to talk a little bit about PowerShell. Now, I think there's probably a fairly common narrative that's thrown around that PowerShell's dead and is no longer used. But I can quite confidently say that in the vast, vast majority of cases that we see, or in incidents that we see, PowerShell is still used at some point. There are certainly some threat actors that will try very hard to avoid using PowerShell, and sometimes they are successful, but the vast majority use it at some point. And that usually unfolds in a few ways. Either they will heavily utilize PowerShell because they believe they won't be detected, or they will be forced to fall back to tooling that they rely on, which is written in PowerShell, or, especially in the case of Cobalt Strike, they believe that they are not executing PowerShell, but they run inbuilt commands in Cobalt Strike which leverage PowerShell under the hood, and they don't realize that they're leaving these breadcrumbs across your estate for you to find. So the three tables I've put on the screen here are examples of telemetry that are generated by Cobalt Strike's built-in lateral movement modules. So if you're a threat actor and you're using Cobalt Strike and you want to move from machine to machine, Cobalt Strike offers a number of modules such as WinRM and PSEXEC to move from machine to machine, to enable that functionality. And the three examples I put on the screen here show the telemetry that's generated. And the really important components are the bits that I've highlighted in red. So the top table is the telemetry that's generated on the source machine when you use the WinRM lateral movement. So this is a machine that the actor's compromised. They're moving from this machine to a target machine. When they run the WinRM lateral movement module, you'll see PowerShell being created with the executable arguments -nop, -exec bypass, -encoded command, and then a long base64 encoded string. Now, straight off the bat, there are some really interesting keywords here that we would want to detect. We would look for the presence of -nop exec, bypass, encoded command, and then we probably use some regex to determine the presence of a long base64 encoded string. Now, what we wouldn't do is try and tag on the whole part of that string, because as Tim talked about in his presentation, you don't want an actor to change a little bit and that break your entire detection technique. So we tag on each part separately and then aggregate those results together. We also, whenever we see a base64 encoded string, we'll try and automatically decode that, because base64, the encoded version, doesn't give you very much context, and context is king in my eyes. So we will try and decode that content and then tag on the internals. So on the far right column in the top table, you can see the decoded base64 content. You can see IEX, invoke expression, new object, net web client, download string. These are all opportunities to tag in more granular depth. In the middle table, you've got the PowerShell that's created on the destination machine. So we've got telemetry that's generated on the source and also on the destination. And we can see WSM prov host launching PowerShell with this fixed string, version 5.1-s-no logo -no profile. And we have a specific detection for that. That's one of our more specific ones for Cobalt Strike. And very commonly, if we see that exact pattern of that parent and child with those executable arguments, we know that Cobalt Strike's in use and it's being used for lateral movement.
To just kind of illustrate this a little bit more, we wanted to kind of bring this to life. So in an incident response engagement where we were called in by a client who'd had a notification from a CERT saying that they'd been compromised by a threat actor who'd been on their systems for at least 20 days prior to this kind of engagement, we went in and kind of rolled our EDR agent across the full network to kind of gain that visibility and really understand what was going on. This detection that James has talked about, this version 5.1 kind of profile kind of string, it's one that screams out to me as someone who's done incident response before quite a lot. You just see it in a log and you know exactly what it was. In this incident, in this case, it was invaluable. It allowed us to have that signature and sort of detection and intelligence that we built on our back end to rapidly detect this across this entire network. In this instance, the threat actor had actually got Cobalt Strike on 224 unique hosts across 5 domains. This is like a large network. The actor had a lot of inbuilt access and sort of access to this client and victim at this point in time and was very close to rolling ransomware. The ability for us to respond to this quickly and speed through these kind of detections was key in avoiding the actor actually rolling ransomware in this instance. Personally, this was one of my favorite incident response cases because as part of containment, I got to sit there on our EDR console and click kill beacon a lot of times. And actually being able to fight back and do that is not something we get that common. And as an incident response, it's usually kind of, everything's gone wrong and you're called in to find out what happened. Kind of increasingly more common, it's kind of something's wrong and let's avoid something worse happening. So this is really showing you kind of the value of these detections.
So while we're talking about lateral movement, I want to touch on one more module, which is the PSEXEC module of Cobalt Strike. Of all the lateral movement modules that we see being used, this is by far the most common one. So I thought I'd talk a little bit about how this module works. This is kind of what we'll do when we're approaching detection. We'll put Cobalt Strike in a lab, emulate it, and then build detection capability. So on the left, you've got a machine that's been compromised, and a threat actor is using Cobalt Strike to execute commands on that machine. And on the right is a machine that they want to move on to. That's their target. And the way that PSEXEC works is that as long as they have appropriate permissions, you'll connect to that target machine, and you'll write an executable file into the admin $share on that target machine. You'll then remotely create a service on that target machine and execute it. And all that service does when it executes is it essentially just runs that file that's been dropped in the admin $share. That remote service is then removed, and you now have a Cobalt Strike beacon running on the target machine, and the threat actors managed to move from machine A to machine B. Now, when we looked at this in the lab, we found that this generates some quite predictable behavior. And this is one of those techniques, one of those detection opportunities that can't be easily changed by the malleable C2 profile. So threat actors may use this, thinking they're not leaving an easy trace, an easy opportunity to be found, but actually, they are. So if we look at the table at the bottom, this is the telemetry, or examples of telemetry that's generated by this technique. So moving from left to right, we can see that the payload is always dropped to the top-level directory in the admin $share. In the middle column, we can see that the naming convention of the executable file is always consistent. It's a 7-character alphanumeric executable. And then on the right, we know that it's going to be executed by a service, and therefore the parent process is going to be services.exe. By tying these three things together, we can build a really powerful detection rule. So if we look at the box in the top right, this is some example detection logic, some pseudocode, if you will. And we're just looking for those three criteria. We're looking for services.exe, executing a 7-character alphanumeric executable that exists in the admin share. These three things combined together will allow you to detect Cobalt Strike's PSEXEC lateral movement. And that's a specific detection. But as we've talked about during this presentation, we want to take that one step further and maybe make it more generic. So a great detection hunt that we can do, but also detection ruling that we can do, is just to look for unusual executables, not specifically 7-character alphanumeric, but just unusual executables being launched by services.exe. And I'm going to talk a little bit about memory artifacts. So this is going to get a little bit technical, but I think it's well worth the time to talk about. Memory artifacts is by far one of the most valuable detection opportunities that we've built over the last few years, and has proved time and time again to be worth its weight in gold to us. So we've got a kind of niche example here, or niche example, where you've got the user Bob who's downloaded clickme.exe. And when I named this person Bob, I actually wasn't aware that Tim was going to use Bob. It's not the same person. So we've got clickme.exe that's been downloaded. And I think if a threat actor managed to achieve that and a user ran clickme.exe, I would hope that blue teams would find that fairly quickly. It's running out of the user's downloads folder. It's unsigned, probably. It's come from the internet. And it should be a fairly dead giveaway that something suspicious is going on. So threat actors using Cobalt Strike and other frameworks will often try and move into a clean process to exist in. And that's what they're doing here on the right. So the default spawn to of Cobalt Strike, rundl32, it will create an instance of rundl32, allocate a memory region in that process, write the payload into that process, and then exist in rundl32, a nice, signed, clean Windows binary. Typically then, clickme.exe would go away, and there would be no dirty artifact for the blue teams to hunt for. So knowing that Cobalt Strike and other frameworks do this, we need to pay attention to what lives in memory. And you can get visibility into memory in a few different ways. You could tap into certain ETW, event tracing for Windows feeds. You could use a memory scanner, or you could hook certain APIs. All of these will allow you to get visibility into what's running in memory on your system. And once you've got that capability to look in memory, you can start looking for certain artifacts and breadcrumbs, if you will. Now, by default, Cobalt Strike will actually inject certain strings into memory, such as beacon.dll and beacon.x64.dll. Now again, these sound like low-hanging fruit, but I've talked about quite a few of them so far. And what we found is that threat actors may change one of those things, but they very rarely change all of them. So if you layer these low-hanging fruit together, it becomes quite difficult for the threat actors to remember to change them all, and they'll often get caught through this. So we've had a lot of success at some very high-end threat actors that have left beacon.dll or beacon.x64.dll in memory. And I'm sure if we told them this, and their beacons hadn't just died, they probably would have kicked themselves a little bit. We can also look for memory permissions, and this is more of a generic threat hunt that we would do that would lead into an investigation. So when we look for the regions in memory that have been created, one of the biggest giveaways we can look for is memory permissions of page, execute, read, write, RWX. This in and of itself isn't a perfect example of malicious activity, but it could be a giveaway that it's something that we want to investigate further. Maybe we would dump that memory region, look at what that process is doing, and look for signs of unusual activity. Now, threat actors know that we like to hunt for RWX, and to get around this, Cobalt Strike actually exposes a setting in the malleable C2 called use RWX, And by default, it's set to true, and it will use RWX. But you can set that to false. And when that happens, it will create the memory region as page read write, RW. And then before executing it, it will change it to page execute read to avoid, at any point, RWX being used. So that's something that the threat actors have done to try and remain undetected. But for us as defenders, we can use that pairing as a stronger indicator of malicious activity. So again, via memory scanner or an ECW feed or by hooking APIs, looking for memory regions that were created as page read write and then were changed to page execute read before execution, that can be a good sign that someone's trying to avoid using RWX and avoid detection. We can also look at the content that exists at the start of these memory regions. So at the top, we can talk a little bit about malformed PE headers. And I've put an example that I've tried to highlight in red. Now, when Cobalt Strike injects itself into memory, it will inject a PE file. And at the start of every legitimate PE file, you'll have the same 2 bytes, MZ. That's legitimate. However, the next 4 bytes shouldn't be ARUH. That's considered to be a malformed PE header. So the presence of those 6 bytes, MZ, ARUH, is considered to be a malformed PE header, and that's hard-coded into Cobalt Strike. I think that's one of those default indicators that we can use. We see very few threat actors changing this. So looking for the contents of a memory region where you've got this 6-byte pattern can be a great way to detect Cobalt Strike. To build onto this, we do see some threat actors that do change this. And what we've seen is that a lot of them will actually take their kind of evasion a little bit too far. So if you look in the bottom image, you can see that they've removed ARUH. They've also removed MZ. And we think what they're trying to do here is say, well, we don't want the defenders to know there's a PE file in memory. But if you scan a little bit further down this image, you'll see a fairly big giveaway. This program cannot be run in DOS mode. And so a really powerful detection that we've built is look for other characteristics of a PE file, like this program cannot be run in DOS mode, and then just check, is that MZ header present? And if it's not, again, we think that threat actors are trying to avoid detection, and it's a great indicator for us. Again,
to bring this a little bit to life, earlier this year, we had an incident response engagement for a victim in the UK who'd been compromised with an abelian threat actor. We were called in to explore and find the kind of full scope of that kind of compromise, and so we rolled our EDR agent again. In this instance, and as I kind of touched on earlier, they had highly configured Cobalt Strike. They had changed a lot of the default settings. They'd done it in a way so it wasn't the same as used in any other Nebelium intrusion that was kind of publicly discussed about or in our other kind of private communication with kind of peers. But we were able to catch them very effectively with this memory artifact technique. They hadn't changed the page permissions. They were still using RWX, and they had left the beacon DLL string in there. So this triggered across all the hosts they had coverage of, and we backed this up with further forensics kind of on these boxes to make sure we hadn't missed anything. This kind of really evidences how this can be valuable, not just for your basic kind of normal actors, but sort of ones who want to kind of modify that, and the value for kind of targeting these techniques, as James says, that the actors are either not aware about or is difficult for them to change. To kind of then add in like another aspect to this, I spoke earlier about our kind of ransomware victim. In that instance, this also was really useful, not only for detecting Cobalt Strike, but also for detecting an APT implant that had been sat on their network for 2 years. This technique, whilst it didn't have the beacon DLL strings, they still had the page permissions that we look for suspicious in-memory implants, and allowed us to detect that as well as Cobalt Strike, showing that detecting these kind of indicators for Cobalt Strike can also have transferable kind of relevance for other kind of offensive frameworks and implants used by other actors.
I think this is the last detection opportunity that we're going to be talking about, which is network indicators. Now, when we think about network telemetry, we tend to think about it from the firewall or the proxy perspective. And that's great. That's a really, really powerful data source to have. But when you trace that connectivity back, you can typically only trace it back to an endpoint as a whole. As endpoint telemetry has developed, we've realized we can actually get network telemetry directly from the endpoint itself. And this can provide a much richer picture, because we can actually trace the telemetry back to individual processes or even threads within those processes, which opens up opportunities for better detections, but also better noise reduction, which means we can write higher fidelity detections. Now, when Cobalt Strike exists on a network, it will, through various different mechanisms, and I'm sure Alfie in his talk later will talk about some more interesting command and control mechanisms, but typically there will be some form of command and control. And in the example you can see here, you've got a victim machine talking to the domain attakai-technologies.online. I think I actually borrowed this from an incident that we saw about a year ago. That is a legitimate example of a ransomware domain that was in use by a threat actor. But the really interesting part is the bit that I've highlighted in red, which is /visit.js. And that's randomly appended by Cobalt Strike depending on the profile. And this is the kind of example telemetry that we can see, and that if you look at from the endpoint perspective, the richness of that telemetry. We don't just know which endpoint is connecting to attakai-technologies.online or .website. We know the executable, so winlogon or rundl32.exe. So knowing that Cobalt Strike will kind of make this outbound network activity, we started thinking about how we could detect this. We've talked a lot about the Cobalt Strike profile, and again, I'm going to bring it into this slide and talk about the default profile, so in the bottom left. So if you remember in that last slide, there was the /visit.js that was highlighted in red. There is a series of paths that are listed in the default profile, which will specify which path to use when it's performing network communication. These can be changed, but again, we often find that they aren't. So what we started looking at is, if we do some basic filtering and remove things like browsers and email clients, how many legitimate processes on an endpoint make connections to domains which use these paths? The answer is very few. So with some fairly light filtering, we actually found that we can effectively hunt for Windows executables that are communicating to external domains using paths that are specified in the default Cobalt Strike profile. And this has proved to be a great way that if we don't get the initial execution, as soon as it starts beaconing, we get an alert and get a detection that says, hey, this looks like Cobalt Strike beaconing behavior. Now, this can be changed via the malleable C2 profile. And Callum talked about a bit in his part of the presentation about known and unknown configs. And there are a huge number of configs that are available online that do customize this behavior. And some of the most popular ones mimic jQuery, and it will hard-code a jQuery path. But the same logic applies here. Once you filter out browsers and you filter out email clients, there aren't actually that many Windows processes that make network connections using that jQuery path. So my recommendation here would be, go and put this in your environment and see, does it stand out? With a little bit of filtering, can you remove the commonalities and build a good detection? So all we're detecting on here is the use of commonly known Cobalt Strike paths in network connections.
Thanks, James. So what do we want you to take away from this talk? Well, a few key things. To start, a real appreciation that Cobalt Strike is a prevalent tool used by many threat actors that are very relevant for you on a day-to-day basis, and it is something that's important to detect. It is highly configurable, but it's often used with defaults or very kind of known configuration in the wild that present significant detection opportunities. You can detect Cobalt Strike effectively at scale. There's a kind of myth or some talk in the industry that you can't. You can. We do this on a day-to-day basis, and if you kind of take some of the learnings from our talk, there's definitely stuff you can implement yourselves to do this effectively in your own environments. You should focus the detection very much on high-fidelity indicators. So we talked a little bit about some of those that are through some of the known config, but also focus those more towards things that the actors can't change or things they find very difficult to change. That will give you a long-term return on the value of kind of that time investment in building those detections.